Hello and welcome back to Let's Code Physics. We have had a lot of great progress in this series so far in developing these graphs of the electric potential for different charge distributions of different surface charge densities. This was the one we got at the end of the last video. This is an example of a quadrupole where we have this charged square. It's a little squished, but it is a square if you check out the units, if you check out the axes on the side. So this is a charged square with positive charges in these two corners and negative charges in these two corners, and lo and behold, you get these two peaks, get these two valleys off of these corners, and you get some interesting geometry, you know, some saddle points and things like that in the middle. As a reminder, we're leaving our charged object just as a flat potential here because we don't want to divide by 0 when we go integrating in there, so we're just not going to even try integrating there. So this is really neat. This is a result of our code here that evaluates the charge density, the distance between the source point where the charge lives and the field point where we're measuring the potential, and places all of that together into this integrand that we're integrating over. And then we're looping over various values of the field points. So we're going around these values of x and y, that's the field point, and then for each one of those points we perform an integral here to get the potential. That's the x prime and y prime, and then at the end it integrates it all for us. And this is a wonderful code. This is a wonderful way to visualize these electric potentials, but it has the disadvantage that we're having to generate the integration points as we go. In other words, when we go down to our integral here, right now we're limited to just rectangles. If we wanted to do a circle, for example, we would have to recalculate y prime min and y prime max for every x prime loop. And we can do that. We know the equation of a circle. We could even do something complicated like an ellipse. We could even do something complicated like a right triangle. But suppose you wanted to do a like a hexagon, so a various sided polygon, or a what do you call it with 7 sides? Is that a septagon? A septagon. If it's a former septagon, does that make it a D-septagon? All right, I'll show myself out. Or if you wanted a nonagon or something that, you know, wasn't quite so nicely implemented in terms of an equation, you can still program it, but you'd be having to go in here inside the actual machinery of the integrator to change that every time. So what I've done is I've copied this code, our potential integrator. I've copied that code over here into this potential integrator-shapes.sce. And so the way this code works is a little bit differently. Instead of calculating the points to integrate, it's going to ask you for what points you want integrated over. So it's going to ask you for a set of x points to integrate and for a set of y points to integrate. And so those are the points that it's going to be looking over. It still assumes those are spaced out by the same dx prime, dy prime values, but this code doesn't create those points. It assumes that those points come from somewhere else, and that's where we go into our new shapemaker.sce code. So what I've got in this shapemaker code is several different functions for making various shapes. So the first one we'll try out is this make rectangle, because we already know how a rectangle works. We already know what that should look like, and so we'll start with this. And you always start with a case that you know what the answer needs to look like. And so for make rectangle, you just tell it the minimum x value, so how far over in the x direction you want it to go. The y minimum, so how far down in the y direction you want it to go, x max, how far to the right in the x direction you want it to go, and y max, how far up in the y direction you want it to go. And I'm having to declare some global variables just so that everybody's on the same page. All these functions and the main program are on the same page with x points to integrate, y points to integrate, n points to integrate, dx prime, dy prime. Notice those are the same names that we use in potential integrator, which is why I've added this statement do not clear, so we can't use a clear command up at the top here, or else we'll lose all those lovely points we generated here. So what I'll do is I'll come down to the main part of the program here. We're going to make a rectangle that goes from the corners -1, -1 to the corner -1, or excuse me, 1, 1, and then the other combinations form the other corners. I've also added in this plot2D command so that we can visualize what those points are, because after trying this multiple times, it is really irritating running this thing and then having to run the potential integrator just to see whether you got the shape correct. So I found the plot2D graphing command, and so we'll be using that. Just as a technical note, at least from what I've been able to see, when you use the surf command over here, it actually uses a left-hand coordinate system, which technically doesn't matter, right? You're still getting the same graph, but in terms of matching it up with X, Y, and Z in the way that we teach students to in our classes, I'm swapping the X points and Y points here. If you download this and you find that that's not the case, or you don't care, feel free to comment this out. That may be an artifact of the PlotLib library that I installed. I'm not sure yet, but I just know that this works, so I'm leaving it in for now. So let's see if we get a rectangle like we expect to. Lo and behold, we do. Of course, it is zoomed in exactly to that rectangle. So let's give that a try over here. So that should be the same type of rectangle that we've had before. Let's leave it at a uniform charge density for right now. We'll go out. We'll make the viewing box 3 times bigger than the rectangle. That sounds good. It's technically a square, but we know that all squares are rectangles, right? And this thing will take just a minute or so to run, so I will cut here and enjoy some tea. While this thing is finishing up running, there is one thing I forgot to point out, which is how we're avoiding the charged area. Basically what we're doing is we're checking over this loop, over the integration loop, which we only need one of now, by the way, because we are searching through this set of points. I mean, it's still an n by n loop, and so it still takes a square amount of time to go. But what we're doing is we're checking for whether x is too close to x points to integrate compared to either dx or dx prime, whichever is bigger. Same thing with y minus y prime. Oh, look, and now we're finished. And so here we got our square, our rectangle, and we've got the same type of thing that we saw last time, which is encouraging. So this tells me that this thing is working out well. I'm not entirely sure why I have a blank graph window there, so we'll exit all of our graph windows for next time. Let's see, that worked out well. The next thing that I wanted to do was to make any sort of polygon. And I went through a few iterations of this. Geometry is not my specialty, especially, coding geometry and things like that. So I've outsourced this. I'm going to be pulling in another code. The way this make polygon works is that you ask it to create a polygon with various x corners and then various y corners, or vertices, excuse me. So you've got the point 1, 0, the point 0, -1, the point -1, 0, and the point 0, 1. Now, one thing I have learned with this code that I've pulled in, these do need to be in order of going around the polygon. So you can't go from one vertex to the opposite vertex, down, and then up to the opposite vertex. It does not work that way. You're going to have a bad time. So if I go up to the make polygon, it's got the same global variables as before. It looks for number points just to make sure that, just to take care of any case somebody gave us mismatched arrays. And then it looks for the min and max of all those points. So it's putting a rectangle around the entire polygon. And basically that's going to form our search. So it's searching along the x and y from their minimum and maximum values, and then it's checking for whether that point x and y is within the polygon. Let me maximize so we can see that better. And of course it scrolled on me. There we go. And so it's checking for whether the point x and y is in the polygon made by these 2 points. And if it is, then it adds that point to the x points to integrate. If it doesn't, then if it doesn't, nothing happens. It's also checking for whether the point is new. Let's take a look at that in just a second. First, I want to show you this point in Polygon. This is really cool. This is a code that allows you to check whether this one point is located within the polygon created by these vertices here. I pulled this off of the Scilab file exchange. This is created by David Adams. Thank you, David Adams, for sharing your geometric and programming insights with the community. And basically what this does is it returns either a true or a false, which Scilab knows as a 1 or a 0. As to whether the point is in the polygon, it does this with this line test right here. So it goes through all these different combinations, and so I'm thankful to David Adams so that I did not have to go through and figure all that out or look all that up. But you notice it's comparing pairwise, so it's going the previous vertex and the next vertex, so that's why those have to be in the appropriate order. It will also, if you set this up as an array, tell you whether it's on the edge of the polygon. I didn't think that was necessary to get one more layer of points. I think just having the interior will make the point just fine. Thank you, folks. I'm here all week. It is a Monday. I'm recording this on a Monday. I have to get my puns warmed up for class for the week. The other thing I had to add in is under the consideration of if I've got multiple shapes, checking for whether the point you're considering is new or whether it's already been added in by another shape. And so what this checks for is it returns a true or false as to whether the point you're considering is new. And so what it does is it's considering the current point that you're looking at, x comma y, compared with the points that are already there. And I gave it a little bit of a safety tolerance so that it can be, let's see here. Oh yeah, so that it throws out anything that is within 90% of dx prime or dy prime of the current point. So that way it will only keep points that are substantially new. Let's see. So that will allow us to create polygons. So I've made another rectangle here. So let's run this and check that. Only this time, it's not a rectangle. Well, I mean, this one is a rhombus. I'm tilting you can't see it because I don't have my webcam on, but I'm tilting my head to see if that does make a right angle. Intuition tells me that it might, but intuition also tells me not to rely on intuition. Experience tells me not to rely on intuition. There we go. So I can now integrate over this thing. So let's see what that integral looks like. That potential, excuse me. The potential is the result of the integral, but it's many, many integrals. Okay, here's our result for our rhombus. So you can see it's so here we've got our axes, so it's definitely rotated. It looks very similar to the nicely aligned square that we had before. Just keep in mind, that the jagged pattern, that's not really there physically. That's just a result of the mesh that we're imposing. We could increase the number of points to integrate and make this much finer. That would come out a little bit cleaner. But for the sake of time, I'm assuming we get the idea of how it works there. So that is really neat. The next thing that I wanted to try out was making a circle. So polygons are great, so we can make all sorts of sided polygons. And for the next video, I'm going to be making heavy use of this routine. And if you stick around to the end of the video, I'll give you not a preview. I'll give you a description. I'll give you the teaser for what that is. So the next thing I wanted to do is to be able to make a circle. In order to make a circle, you've got to give 3 pieces of information. You've got to tell where the center of the circle is located. So x center and y center, and then you've got to give the radius of the circle. And so this just loops over using the equation for a circle. So it's taking that y is going to be anywhere between the the top edge and the bottom edge of the current slice that you're at. And so that's going from y center minus this amount here to y center plus this amount here. So these represent the edges of the circle, where you've got square root the radius squared minus how far along x is squared. So that's x minus x center squared. So if you think about rearranging this, you have y min minus y center equals square root radius squared minus x center squared. So if you if that's If that's difficult for you to visualize, just think of x center and y center as 0. So your circle is centered at the origin, and that will give you a circle of radius centered at the origin, and you get the usual equation for a circle: x squared plus y squared equals a constant squared. And so then it just goes over the same loop. And so this is, again, so that we don't have to put all of this stuff into the potential integrator. We can leave this thing alone, except for the xmin, ymin, xmax, ymax stuff, and then just play around with this to get our different shapes. And so what I can do now is I can make a circle. Let's have this thing be at 1.5 over, 0.02 up, and a radius of 1. And the reason I picked this as an oddball number is because I wanted to be able to do this and make a rectangle and make sure that the points were not being double counted. So here we've got our circle. Again, it looks a little squished because the axes are not quite the same. Yeah, that's even worse. And so here we've got our circle. All right, cool. The next thing we might be interested in is making an ellipse. So ellipses are squished circles. Well, really, a circle is a perfectly symmetric ellipse. For an ellipse, you've got to provide an additional piece of information. You've got to give the center just like you had before, but then you've got to give what the radius is in the x direction, what the radius is in the y direction. If I were a good geometer, I would call those the semi-major axis and the semi-minor axis, but I prefer to think of them in terms of which direction they're going. So we've got our y min with a similar equation like we had before, only now we're scaling y by y radius and scaling x by x radius. Same thing down here. And so that's going to give us an ellipse that is 5, that has a radius in the x direction of 5, a radius in the y direction of 1. So it should be 10 wide and 2 tall. It's TWO tall, not more tall than it should be. There it is. And of course, now I need this thing to be stretched out a little bit. So you notice this one's going from -5 to 5, and vertically it's going from 1 to -1. So we've got our ellipse here. So let's have a little bit of fun with doing some charges on this thing. Let's do our make circle. Let's have this thing be centered at, insert unlock, there we go. Centered at 0, 0. And we'll give it a radius of 1. All right, cool. And then let's go down, let's go over to here, and let's see, we have an idea. Let's go ahead and do, we have an idea of what it's going to look like with uniform. We've been doing uniform for a while. I want to see what the circle looks like when we do this number, when we do this quadrupole charge density. So let's see. So we've run our shape maker. Let's run it again just to be sure. There we go. Good. Because now it's going to feed those data points into our potential integrator code. Yes, I'm happy with those boundaries. And so I will cut here and see you in just a second. Alrighty, so we've got our circle in the middle there. It's a circle of radius 1. Yep, it's going from -1 to 1 in every direction. And we've got our quadrupole shape like we had before. It's making, I mean, it's the same general shape, but it's making a rather, it's looking a bit different. Let's zoom in or maximize the view. There we go. So this is pretty cool. Yeah, so we've got, it seems to be accentuating the curvature a little bit more than the square did, which would make sense. Although we are imposing it as sort of a Cartesian distribution on a circle, so that's kind of neat. Let's see what happens. Let's do this. Let's now have the charge distribution be polar in nature. So let's say, for example, we make this thing a function of the angle that goes around. So let's see, if I want to retrieve the angle, I would need to take the arctangent of y prime over x prime. Do I want to? Yeah. Arctangent is fine because, well, I will have to worry about dividing by 0 at x equals 0 and y equals 0, but let's see whether that's a problem. It'll complain at me very quickly if that is the case. Oh, yep, division by 0. All right, then we'll just have to exclude those points, I suppose. So if x prime greater than 0, then make this calculation. Otherwise, we'll just make it 0. Oh, and I need an s equals there anyway. Here we go. Let's see here. End-if, or not end-if, end. There we go. Because that'll be like 2 points that we don't include. That's not going to make a huge contribution. Okay, cool. And we are marching right along. I will see y'all on the other side. All right, cool. So now we've got our charge density varying like the angle going around. So it'll go from 0 to it'll go from, let's see, it's got a 0 twice. Oh yeah, it'll have a 0 twice because y is equal to 0 twice. So it's going from 0 up to pi over 2, or 0 to pi over 2, and 0 to negative pi over 2. So you notice we get a dipole structure, not the quadrupole structure, but a dipole structure. So that's pretty neat. And so the charge density is now going, or the potential is now going around like a circle. You could follow this on, sort of a, I guess that would make a, I don't know if that would make an ellipse. If you were to trace, a contour around here, what kind of shape would you get? That is something I don't know how to evaluate analytically. That would be a fun thing to try to do, though. Okay, so let me, in our last couple minutes, give you a preview of what we're going to be looking at next time. So this video is scheduled to go up on December the 7th. And so the next video will go up December the 14th. That'll be the last video for season 3. I'll take a little bit of a holiday break and then come back in January with some new series. But what I want to finish out with, since it is the holiday season, is some trying out some different shapes that are holiday related. I've already made a Christmas tree shape, so I'll show you how the points end up today, but I won't show you the potential. I want you to come back next week to see the potential produced charged Christmas tree. So you imagine you've placed charges on your Christmas tree. I don't know why you would want to do such a thing, but let's say you've decorated your Christmas tree with charged lights and charged leaves and everything. What kind of potential you would get. And so we will be importing this shape. This took me, I guess, about half an hour to get in. I basically had to program in each of these vertices, and so that's the list that you see here are the vertices. And so what we'll do for next time is we'll put these points into the potential integrator. We'll get a look at what the potential produced by a charged Christmas tree is. We'll try some other holiday related shapes just to be as festive as possible. And I think that'll be fun, and it'll be a good way to transition into the holiday break. So thank you so much for watching. I will see you next time. Bye-bye.